Hello, good day. I am James Daniel Falcasantos, and together with my group mates Raymart Soriano and Gian Laurene, we'll be discussing today about the four-layer diode and the silicon-controlled rectifier. For introductions, so a Shockley diode or the four-layer diode is a type of thyristor, which is a class of device constructed of four alternating P and N-type semiconductor layers. So it was invented by William Shockley and manufactured and marketed by the Shockley Semiconductor Laboratory in the 1950s. So when a positive bias voltage is applied to the anode, the base emitter junctions of the Q1 or the transistor 1 and the Q2 transistor 2 are forward bias, and the common base collector is reverse bias. So the operation of a four-layer diode that when a forward bias voltage will act as an open switch or offstate due to the very high forward resistance because this region uh, is in forward blocking region, and this region exists from the 0 volts up to the forward breakover voltage. So when the anode current is equals to the switching current, the forward voltage drop is also equals to the forward breakover voltage, and the internal transistors become saturated. When this happens, the forward voltage decreases to a low value, and the diode enters the forward conduction region or the on state. So when this happens, the four-layer diode or the Shockley diode will continue to conduct until the current level will drop to a certain level. So holding current is the current level that maintains the on state of the diode. Past this level, and the device will rapidly switches back to the off state and enters the forward blocking region. Switching current, on the other hand, is the current value, where the device switches from the forward blocking region to the forward conduction region. Uh, so another type of the four-layer diode is the silicon controlled rectifier or the SCR. So a silicon controlled rectifier is a four-layer PNPN device with three terminals: the anode, cathode, and the gate, that is widely used in power switching. So larger SCRs can control hundreds of amperes and current. What differentiates the silicon controlled rectifier to the Shockley diode is the addition of the gate. So a positive pulse of current should be applied to the gate, as this will act as a trigger to turn on the transistor 2 or Q2, which also turns on Q1. So as Q1 provides additional base current for Q2, making it always on even when the trigger current is removed. This will also make or provide a path for the base current of the Q1, which makes it always turns on. It can also be turned on without the gate triggering by increasing the anode to cathode voltage to a value that will exceed the forward breakover voltage. So, to turn off the silicon controlled rectifier, or like the Shockley diode, SCR cannot be easily turned off because it stays in the forward conductance region. But there are two basic methods for turning SCR off: the anode current interruption and the forced commutation. In the anode current, uh, in the anode current interruption, a momentary series of parallel arrangement in in the circuit can be made to divert the flow of current, which weakens the flow of current in the SCR, lowering its current level to a certain amount, which will then trigger it to be in the forward blocking region. Now for the uh, forced current commutation, it is done by momentarily forcing current through the SCR in the direction opposite to the forward conduction by using a capacitor. which we can see in the diagram.
Hello, I'm Raymart Soriano and I'm going to report about the light activated SCR or the LA-SCR. This is also called the photo SCR, a silicon controlled rectifier. It is also a four-layer semiconductor that operates the same as a conventional SCR, except that it can also be triggered by light using a small lens to focus on the light onto a sensitive ano light sensitive gate. Can parang it's the same as the conventional SCR, except that it can also be triggered by using a light na itututok mo dun sa small lens para ma-activate siya. Like the conventional SCR, LA's SCR, once triggered, will continue to conduct even if light is no longer present until the current falls below a specific value. So, hindi siya automatically nag-shutdown. Eh, may magsha-shutdown siya kapag mag-fall na yung current in a specific value. It is most sensitive to light when the gate terminal is open. The light-activated SCR is also a temperature sensitive, so it can also be turned on a low light level since current increases with temperature and the resistor is needed from the gate to the cathode to reduce its sensitivity. LASCR are extremely efficient and provides the electrical isolation between the control circuit and the load because of the these LACRs are used in high voltages, high current switching high current switching systems. So this is the diagram of the light activated SCR, which the DC voltage and the light bulb, it will be triggered by using light here. So next, the on-off control of the current. When the S- SCR can be used as a switch like in the diagram where it is off but momentarily closure of switch 1 provides a pulse of a current into the gate. This will trigger the silicon controlled rectifier on so and conducts current through the load resistor. The SCR remains in conduction even after the momentary contact of switch 1 is removed because the anode current is equal to or greater than the holding current. When switch 2 is momentarily closed, current is shunted around the SCR, reducing its anode current below the holding value. This turns the silicon controlled rectifier off and reduces the load current to zero. So the half-wave power control. So a common application of silicon controlled rectifiers is in the control of AC power for lamps, lamp dimmers, electric heaters, and electric motors. So a half-wave variable resistance phase control circuit is a circuit where AC are applied across terminals A and B. So the resistor 1 limits the current and the potentiometer resistor 2, an adjustable variable resistor, sets the trigger level for the SCR. By adjusting the resistor 2, the SCR can be made to trigger at any point on positive half cycle of AC waveform between 0 to and 90 degrees. So when the silicon control rectifier triggers near the beginning of the cycle, approximately 0 degrees, it conducts for approximately 180 degrees and maximum power is delivered to the load. When it triggers near the peak of the positive half cycle, or 90 degrees, the silicon controlled rectifier conducts for approximately 90 degrees and less power is delivered to the load. So R2, by adjusting the R2, triggering can be made to occur anywhere between these two extremes, and therefore a variable amount of power can be delivered to the load. When the AC when the AC input goes negative, the SCR turns off and does not conduct again until the trigger point on the next positive half cycle. So the diode prevents the negative AC voltage from being applied to the gate of SCR. So a useful circuit that uses a similar idea to the phase of control circuit is a motor speed controller. For a DC motor, which can run on AC using an silicon controlled rectifier to control the AC to pulse DC. So the DC motor can outpulse from the rectified AC, so there is no need to add a filter. D1 sets a minimum gate voltage of 0.7 volts, and the R2 adjusts the firing point of the SCR, that the firing point of the SCR. So the circuit can be adapted to the other loads that can be operated with pulse DC, such as a lamp. Another variation of speed control circuit uses a programmable unijunction transistor, or abbreviated to PUT, or PUT.
So, another example of SCR application is a backup lighting for power interruption. It is a circuit that maintains the lighting of the lamp or a bulb by using a backup battery when there is an AC power failure. The figure is a center tap full wave rectifier used for providing AC power to a low voltage lamp. As long as there is AC power available in the circuit, the battery charges through diode D3 and R1. So what will happen if there is an interruption of the AC power? How will the backup lighting for power interruption works? So when there is an interruption of AC power, the capacitor discharges through the closed path R1, D3, and RT, as you can see in the figure, making the cathode less positive than the anode or the gate. This action establishes a triggering condition, and the SCR begins to conduct current from the battery processed to the SCR and the lamp, thus maintaining illuminations. When the AC power is restored, the capacitor recharges and the SCR turns off. The battery begins recharging. So, when there is an AC power available in a circuit, the capacitor and the battery will recharge or charging, and the SCR turns off. The SCR will turn on only if there is a power interruption or there is a power failure. The battery will automatically release some power through capacitor and sends it to the SCR and to the lamp in order for it to remain turned on in order for the lamp to remain turned on. Another example of SCR application is the overvoltage protection circuit. The DC output voltage from the regulator is monitored by the Zener diode D1 and the resistive voltage divider R1 and R2. The upper limit of the output voltage is set by the Zener voltage. If this voltage is exceeded its limit, the Zener conducts and the voltage divider produces an SCR trigger voltage. The voltage turns on the SCR, which is connected across the line voltage. The SCR current causes the fuse to blow, thus disconnecting the line voltage from the power supply. So in this SCR application, from the word itself, over voltage show, which means if the DC voltage exceeded the upper limit of the output voltage that was set by the Zener voltage, then it will produce an SCR trigger voltage, which will automatically turns on the SCR. So when the SCR is on, which is connected across the line voltage, it will cause the fuse to blow and disconnecting the line voltage from the power supply.